By the time we got into the 1920s, 1930s, what people had thought we knew about particles, at least in terms of the particles we knew about, was the electron, proton, and the neutron. These are also the particles that you were quite familiar with at this stage in your science career. As quantum theory developed, more subatomic particles became known to us. So we just kind of want to explore that just a little bit. So the first name that kind of comes up when we're talking about these new particles, or what we call this antimatter, is a gentleman named Paul Dirac from the UK. He predicted the existence of these new particles. He just kind of said they were a little peculiar. One of them being this thing called the positive electron. And he got this through this equation that he had developed through Einstein's theory of special relativity, Schrodinger's wave equation, all that lovely stuff. Now, you don't have to know this equation at the high school level. This is a graduate level physics thing. We just included it in there for a little fun, a little scare factor. But here's the thing. Dirac predicted, theoretically, that this positive electron has to exist. Now, what we have to wait for is we have the theory. We need to determine this experimentally and verify it. And that came a little bit later. And this came from a gentleman from the United States named Carl Anderson. So if you look here, you'll see this cloud chamber. And you'll see these two particles sort of branching out from a common point. Now, Anderson knew one of these was an electron. What that told him is that this other particle that was there, it had to be very similar to the electron. It had to have the same mass. All these properties have to be identical with the exception of the charge. What he knew is that the charge had to be opposite that the electron. So the electron being a charge of minus 1e, this new particle had to be a charge of plus 1e. What Anderson had discovered with this photo of this chamber, he had discovered the evidence, or he had discovered the existence of this positively charged electron, this positive electron. So he had validated findings that Dirac had made just a little bit earlier. So this positively charged electron, the name we give it here is the positron, and we would call this the antiparticle to the electron. So for his work, Anderson was awarded the Nobel Prize in 1936. Now, the reason that we like to study particle and antiparticle interactions is that when they collide, they go through this process that we call annihilation. Now, in annihilation, it kind of looks like the particles are effectively destroyed, but we can't actually do that because you can't just have mass disappear by the laws of conservation of mass, and you can't just have energy disappearing by the law of conservation of energy. So what's going to happen is that energy that came in prior to the collision, that is also going to be taken away in some other form. Now, what generally happens when we have a particle-antiparticle collision or a particle-antiparticle annihilation, we're going to have energy being released, and it's going to be generally released in the form of two photons. And those photons, they're going to travel in opposing directions to conserve momentum. And let me explain what's going on with that in this example here. So we want to calculate the energy of a high energy photon from a positron electron annihilation. So kind of just to show you, here's what's going on. So in terms of a before picture, we have an electron coming in, it's going this way. We're going to have a positron come in, also this way. Now you have to understand that the electron and the positron, they have the same mass. We're going to assume that they're traveling towards each other with the same speed. So this has a momentum mv, this has a momentum negative mv, so the total momentum before this collision is going to be 0. Now, after the fact, those particles, they're going to annihilate. I don't know what I drew there, we'll call that some sort of annihilation. Now the thing is, if we had no momentum beforehand, we're going to have no momentum after the fact. So what's going to happen is, after this collision, we're going to have two separate photons that will carry away the energy of that antiparticle-particle collision. And this is the importance of why we need two photons. If we had no momentum before the collision, we have to have no total, if we had no total momentum before the collision, we have to have no total momentum after the collision. If, for example, we had only had one photon, well, that is going to have momentum E over C. We need to have something that counterbalances that exactly, because again, we want to have momentum as 0. What our objective is to find what is the energy of those photons. Well, we know the relationship between mass and energy thanks to Einstein. So we know that E is equal to mc squared. Now in this case we have the electron and we also have the positron. Now what I'm going to do to just simplify this, because I don't like writing out a lot of terms, I know the mass of the electron and the positron, they're the same, so I'm just going to call that some generic mass m. So really what I have here is I have this 2 mc squared. So I get an mc squared from the positron, an mc squared from the electron. So we get 2, we got our mass of the positron and the electron, and then we have that speed of light squared. When you're calculating these, the big thing to watch out for, as always, don't forget your square on the speed of light. That's always a quick trap to get people. And I'll deal with the sig digs a bit later. Now what I'm getting here, to apply some context to it, so this energy, this is the total energy of the system. So this is the energy of the electron and the positron combined. So it's about this 1.64 times 10 to the minus 13 joules. That total energy, this is going to be carried away by 2 photons. What we've been asked is what is the energy of one of those photons? So if we know they'll both take this amount, each one's going to take exactly half of this. So the energy of a single photon is half total energy. So the energy of the photon is going to be about that 1.6398 times 10 to the minus 13 joules. And then we'll divide that by 2. And there's not really a lot of direction in terms of significant digits here, just because, well, I guess I didn't put them. We'll put 3 just to be safe. So we're going to say that each one of these particles, we're going to say it takes about 8.20 times 10 to the minus 14 joules worth of energy. And then of course we could certainly follow up with that calculation from stuff we learned in the previous units. You know, you could be asked to determine the frequency of that photon, wavelength, lots of ways that we could ask that. And that's a pretty common question on the diploma, to ask about energy released in a photon in a particle-antiparticle collision. So the last thing we just want to kind of touch on is we have kind of the known particles that we've talked about already. So we have the electron, the proton, the neutron, the neutrino. So these are kind of our 4 major particles we've discussed in Physics 30, and they each have particular symbols associated with them. So we got the E minus for the electron, usually the P or P plus for the proton. The neutron usually have an N. Sometimes you might have N0, depends how you want to write it. In the neutrino, we have this nu symbol, looks kind of like a hooked V. And also I should add, the proton, sometimes we just put P. All of these particles have their respective antiparticles. So we've already talked about the electron having an antiparticle, which is what we know as the positron. So the symbol for the positron is going to be E+. Same properties as the electron, just positively charged. The proton, it will have its own respective antiparticle known as the antiproton. So we can say it's either P minus, or sometimes what we might do is we might put P bar. The bar tells us that it's an antiparticle. Same thing with the neutron. Its antiparticle is the antineutron. We can have the N bar, or sometimes you might see it with the N0 bar, however you want to write it. And of course the antineutrino, we've already seen this one in talking about beta negative decay. So that's going to be our little nu symbol. And of course we're going to put the little bar over it. We are going to have a little bit more discussion about these antiparticles in a little bit, so stay tuned for that.